Hi everyone, in this video we're going to be talking about section 15.2, double integrals over general regions. So if you haven't watched the 15.1 video, check that one out first because that one's over rectangular regions. And now we're generalizing it because not every region we're going to integrate over will be a nice rectangle, and that's what's going to happen here. So the region of integration may have boundaries that are not parallel to the x and y axes. In 15.1 they were nice straight lines on all the sides. So they might not be parallel to the x and y axes, so what that implies is that your limits of integration, when you're doing your double integrals, they actually might involve variables. And this is because the values are changing, okay? If it's not a straight line, like let's say for x equals some number, let's just make something up, like x equals 2, if x is changing, like maybe it's a curved line, well then a variable can be used to describe that. So your limits of integration might involve variables now. So what you start off with here to think about this region that you're integrating over, your region R is what you're integrating over. You partition it into a bunch of little rectangular shapes. And this is a bounded region, but it's a non-rectangular region. And so what you do here is you use the rectangles that lie completely inside R. And then this is how we partition this region. And so let me just show you what I'm talking about when I say completely inside R. Let's take this rectangle for example. Part of this little rectangle is outside R and part of it's inside, so we don't use that one when we partition. This rectangle is completely inside R, so we'll use that. And we pick all the rectangles that the full thing is inside this blue boundary. If part of it is outside of the blue boundary, we're not going to use it for our partition. And so I would do this for the entire region. Now we have our region R that we're integrating over, and we are taking the little rectangles that are completely inside R. And now if we focus on a single point here, this is going to be in the rectangle that has width delta x and length delta y. Doesn't matter if you switch, this could be length and this could be width. And then remember how this goes from the previous section. We have some surface that would be like popping out of the board here, and then we would have a volume with this little rectangle formed, okay? And so what we're interested in is when this norm of a partition, and I'll explain that in a second, approaches 0. Okay, so the norm of the partition, this is just one particular partitioning that I drew with these black grid lines. Now, if I chose to make them smaller, that's what this is talking about here. The norm is getting smaller. The norm is the largest of any width or length of a rectangle. And so let's say I add in more partitioning, I change this up a little bit. Well, just by adding a couple more lines, oops, not very straight, I'm able to fit more of my blue region R inside of here. So I can now include, let's see, this part that wasn't previously included, and this part, and this part. And if I keep doing this, if I make the partitioning to where the width and length is getting smaller, then I'm going to actually be able to cover more and more of R. And ideally all of R is covered. And so as this norm gets small, the largest width or length of any of these rectangles, then this is actually our double integral, okay? And this is the volume. So the sum of all of the little volumes of the rectangular prisms that would pop out of the board here. This is our like height, the f of x sub k, y sub k value. This would be the height like popping out of the board. And then delta a sub k is the width times length, the area of this little base region. So this would be delta x times delta y. So height times width times length gives us our volume. Then we add up all of these little rectangular prisms and we get the volume under the curve here over this general region R. And so this is our double integral over R, bounded by our function f of xy dA. Now talking about volumes, let's start by supposing that R is a region that's bounded below by this function I'm calling g sub 1, and it's a function of x, and above by a different function. I'll call it g sub 2, also a function of x. And then it's bounded on the left and the right by two values for x equals a and x equals b. So that might look something like this. Now, we know x equals a is fixed and x equals b is a fixed number, but g1 and 2, their functions, they don't have to necessarily be straight lines or constant functions. So on the left and the right, my function might be bounded, let me go to blue actually to make it look like our previous region. It might be bounded like this, but on the top, maybe my g2 curve does something like that. Okay, so this is g sub 2 of x. This is a y value. And then on bottom, maybe g sub 1 does something else. It could do the same thing, or maybe it looks like this. And this is g sub 1 of x. Okay, and so my region here, this is R. This is what I'm integrating over. This is my base region. Okay, and so now what we're going to think about is we're going to start by holding x fixed. Okay, so let's hold x fixed. So at one point in this region, let's go ahead and just pick right here. And if x is fixed, think about integrating at this x value. Okay. Now when I integrate a single integral here, the area under the curve here, it's actually the area between two curves. So my top limit of integration would be whatever this g sub 2 value is right here, and my bottom lower limit of integration would be whatever g sub 1 equals right here. Okay, that's for one integral. And then what I do is then I'm going to take my second integral, and that's going to give me this width for x. Okay, and so our volume here, our volume is, if we're going to hold x fixed, we're going to integrate with respect to y first, and our volume is a double integral where y has the lower limit as g sub, what did I pick, 1 for the bottom, and then the upper limit is y equals g sub 2. And then my second integral, when it's time to integrate with respect to x is going to go from a to b. And then this is how I'll find my volume. Notice that the function y is of x, so you're actually going to evaluate this one first, and then what you end up with is you're going to have x in your integrand when you go to your second or outer integral. And then after that, you'll have values to plug in. And we'll do an example with that. Before we get into the example, let's look at another possibility. So now suppose the region R is bounded on the left by x, which is h sub 1 of y, a function of y, and on the right by another function, x is a function of y. And then below and above by y equals c and y equals d. So that might look something like this. You have y equals c. Let's go ahead and put that right here. And y equals d can maybe be there. And so that's the upper and lower boundary of your region. But then the left and the right are functions of y. They're not constant. They could be changing. And so maybe our left function looks something like this. And that's h sub 1 of y. And in the right function, maybe it does something like this. And that's h sub 2 of y. So this would be our region that we're integrating over. Now, this time, if we hold y fixed, so we have some y value that we're going to hold fixed here, and then we're going to integrate, think of your single integral, the area between the curves. So you're going to have this as your right boundary, and this is your left boundary, and so your limits of integration are going to be from here to here, or upper and lower from here to here. So then our volume, our inside integral for our double integral, it's bounded below by x equals h sub 1 of y, and above or to the right by h sub 2 of y. And so because we held y fixed, we integrate with respect to x first. Then after we figure out this area between these curves, then we're going to integrate with respect to x after that. And so, with respect to y after that. So then we'll integrate between c and d for y. So dx and then dy. Now, right before we get into this example, let me read it to you. We're going to talk about Fubini's theorem, a new version. So the example is going to be to find the volume of z, which is a function of x and y, given that it equals 3 minus x minus y, and then its base, which is in the xy plane, has these boundaries that are given. Now, before we get into this example, we learned Fubini's theorem already in the previous section, but this is a stronger form of it, and we can use this in this example. So, just our background real quick. Z, or f of xy, has to be continuous over your region R. And then notice what you have. You have two possibilities here. Your integral, your double integral over R of f of xy. It's the same thing in both of these. So you have two options here. And it just depends on which region you're working with, which one might be easier. And I'll show you on this example, we'll do both. So if our region R, x is bounded between a and b, and then y is bounded by functions of x, you're going to integrate with respect to y first, and then x after, in order to be able to plug in these constants. So x is going to go second, y is going to go first, bounded from g1 to g2, and f of xy dy dx. But what this theorem is saying is that even if you integrate this way, you're going to get the same answer as if you were to integrate this way. So if our region is bounded between c and d for y, and h1 and h2 for x, then you integrate with respect to y later, so this is outside, integrate with respect to x first, and this is from h1 to h2, of your function f of xy, integrating with respect to x, and then y after that. Okay, so we'll show in this example that we're going to get the same answer either way that we do this. Now, looking at this example, let's start by figuring out what R looks like, our region that we're integrating over. So we have a few things going on. We know we're in the xy plane, we're bounded by the x-axis, y equals x is a line, and then the line x equals 1. And so one of our boundary edges is right here, the x-axis, where we know that y is 0. Okay, let me just mention it right here too. We have this point 0, 0. Y equals x is this diagonal line going through this quadrant. When x is 1, y is 1. When x is 2, y is 2, and so on. So it's this diagonal line right here. And then x is 1 is also a boundary edge. So when x is 1, that's where we're stopping this region. So this is R. Let's go ahead and make it a little bit more identifiable. R is what I'm going to highlight here in purple. So it's just this triangle, this triangular region. Okay, so this is what we're going to be integrating over. And so now we have to actually figure out which way we want to do this. And like I just showed you with Fubini's theorem, you have two options, especially in this case. Sometimes one option is much harder than the other one, but this one, each option is going to work out pretty well. So I'm going to show you both. So I'll call it option 1. Option 1, let's see what we know and focus on how we can come up with our limits of integration. Well, we know, what do we know about x? Let's see. For this triangular region, we know that the lowest x is 0, and the biggest that x will ever be is 1. Okay, so in this region, x goes from 0 to 1. Okay, so what do we know about y? Well, in this region, the lowest that y will ever be is 0, the x-axis. But now, if we're keeping x fixed, so notice there's no functions here, these are just constants. We're keeping it between these two fixed numbers. Well, y is going to actually depend on which choice of x we pick. So let's say, if you think about it like this, you might think maybe y, the highest it will be is 1. That's correct, but that's only at that point. Let's say I pick right here, this x value. Well, at this x value, what is my y value? And my y value comes from this function that's this boundary line. So my y value here, well, I know that y equals x. So this is also x. So the upper boundary for y is x. At this point, y is x. At this point, y is x. At this point, y is x, which happens to be 1. but it's a function of x depending on where we pick our x value at. And so the first option we're going to do is to integrate with respect to y first because it depends on x. And so our volume is our double integral. And what I like to do is I like to use the fixed one first just so I get it out of the way. I know that x is going to be between 0 and 1. And so I'm going to integrate with respect to x second. Now I'm going to put dy before that and then look at my limits for y. Y goes as little as 0, but its upper boundary, depending on where we pick x at, is the function y equals x. And then my integrand is my function I was given. So 3 minus x minus y. And once we have this set up, the rest is just regular integration. So the harder part on this is actually just the setup. After that, we are just doing our regular integration techniques. So focusing on one integral at a time, starting on the inside. Our inside integral, we're integrating with respect to y. So every thing that you have here is just a constant unless it's y. So the integral of 3 is 3y. The integral of negative x is negative xy, because this is just a constant. And then the integral of negative y is negative y squared over 2. And we're evaluating that from y equals 0 to y equals x. Now I like to put my variable here for when I'm about to evaluate, and that's because I don't want to get confused where I'm plugging in. I might accidentally, if I don't write this, maybe I'll plug it in for x, but it's actually going to go in all the place of the y values. So we get 3x minus x times x minus x squared over 2. And this is this inside integral evaluated. Let's make this look a tiny bit nicer. 3x minus x squared minus x squared over 2. And now that was this inside integral. We're going to put this outside integral back on. So this equals this. This was from 0 to 1 for x. And now we integrate with respect to x. And so just everywhere there's an x, that is your variable now. So integrate with respect to x. And we get 3x squared over 2 minus x cubed over 3 minus x cubed over 6 evaluated from x equals 0 to 1. And feel free to pause this and work this out. Okay, if you paused it or not, you should have gotten 1 as your answer. So now I'll show you the other option. Now taking a look at the same example, we're going to do option 2. And same region and everything that we had before, we're just going to look at it differently. So my region R, let's focus on y first. Last time we were thinking about x at the beginning. So y, if we look at what happens with y, the lowest y will ever be is 0, and the highest y will ever be is this point here, which if y is x, we know this is 1. Okay, so y is between 0 and 1. So then we ask, well, what happens with x? Okay, and so x, depending on where we pick our y value, let's say we pick right here, this y value, well then I have this point for x, and then my region that I'm focused on right here, I'm only going from right here, my point, to this right edge, this right boundary. And so what we have here is the biggest y will ever be is 1. Sorry, excuse me, x. The biggest x will ever be is 1. So the upper boundary here is actually 1 for x. But the lower boundary, in this case the left boundary, it changes depending on where we're at on this diagonal line. And so my lower boundary is this point here. And we know that this is y, but this is x, and y equals x. So this is just y equals x. Okay? And now I want to write this in terms of a function of y, so I don't want x to be bounded below by x. We know y equals x, so it's bounded below by y, this y value that has this corresponding x value. Now that's going to help us with our setup. Now our volume is our double integral over this region, and so I'm going to start with what's constant first, and I'm going to put that outside. So we know that y is between 0 and 1, and we'll integrate with respect to y after. So that's going to go last. So integrating with respect to x happens inside, and x is bounded below, or on the left, by y, and on the right by 1, or above by 1. And then our integrand is the same as before, our function 3 minus x minus y, and then we integrate one integral at a time, starting with the inside integral. Okay, so I'll just work this one out real quick. We're going to get the same answer we already got because of Fubini's theorem. You can do this either way, option 1 or 2. So we have 3 x minus x squared over 2 minus y times x, because everything here is a constant except for x, because we're integrating with respect to x. And we're going to evaluate x from y to 1. Okay, so we have 3 times 1 minus 1 squared over 2 minus, notice you're plugging this in for x, so y times 1, all of that minus plugging in a y. So we have 3 times y minus y squared over 2 minus y times y. Now, just this step alone makes me realize like this method, option 2, seems like a slightly more work than option 1. So either way we're going to get the same answer, but option 1 seems like a little bit less work because we didn't have to do this part. We had a 0 in our inside integral last time for our bottom boundary. So let's simplify this a little bit. We have 3 minus a half minus y minus 3y minus y squared over 2 minus y squared. We end up with 5 halves minus 4y, let's see, minus 3 halves y squared. Okay? And then that's going to be what we integrate with, we integrate next. And this is going to be with respect to y. Okay, so let me just make this a little bit more clear. This is our integrand now. So then we integrate this with respect to y, and then plug in our boundaries, and we will get the same answer of 1. You can pause this and work this out if you'd like to see what you end up with, that you do in fact get 1. The integration part itself is things you've done in the past, so that's not going to be the hardest part. The more challenging part is how do you actually find these limits for x and y for your boundary. So there's 2 methods, and it depends on which variable you're thinking about first. So we're going to start by using vertical cross sections. So we're going to take a region and consider vertical lines through it. And so that would mean that we're considering y first and then x second. So the very first step I would recommend is to sketch and label the boundaries that you're given for your problem. Once you have a drawing, it's going to help you figure out the rest. So step 2, find the y limits. And to do this, you're going to mark your y values where a vertical line, so you draw an actual vertical line, enters and then leaves your region R. Okay, that's going to help you find your y limits. Once you've done that, then step 3, you find your x limits, and basically this is just going to be a way for you to pick all the x values that include the vertical lines from step 2. So if you can encompass all the vertical lines you can possibly draw from step 2, then those are going to tell you your x values, your lower left and right x values for your boundary. So taking a look at this example here, let's see if we can put these into practice. I've already done step 1. I've labeled or sketched and labeled. Now sometimes you're going to be given some values where these might meet your axes, but I purposefully left them off to show you what to do. So in this case, I have what I would call like an upper boundary here, and then this lower boundary, the straight line. This one's a curved. It's actually the circle x squared plus y squared is 1. And then this straight line is the lower boundary. So now I need to actually know these numbers here. They're going to come up in finding my limits of integration. You can probably tell maybe by looking on some of these, but I want to show you the process. This point would be where these 2 boundaries meet. And so basically you solve by knowing the fact that they meet there. So you can substitute, if they meet there, they're equal there. So So we're going to substitute one into the other. And I'm just going to pick this one, it's a little bit nicer. So I'm going to take this boundary, and I'm just going to solve, I'll go ahead and solve for y. So if I solve for y, I'll subtract x. 1 minus x is y. And then I'm going to take that and substitute it into my other boundary, since they meet at that point. And so I get x squared plus what was y is now 1 minus x, quantity squared, equals 1. And then I just solve for my variable, in this case it's x. So we get x squared. If you FOIL this out, you're going to get 1 minus 2x plus x squared equals 1. Subtract 1 from both sides. Combine like terms. You have 2x squared minus 2x is 0. So then if I factor, I'm going to be able to find my x values. If I factor out a 2x, I get 2x times x minus 1 is 0. So I know that x is 0, which I can tell because it's on the y-axis here. So x is 0, and then x is 1. So this is 1. Now I actually want this point here. And so if I know that x is 0 here, if I just plug it into either boundary, it doesn't matter which one, I'll go here. X is 0, so this is y equals 1. And so sometimes you'll be able to tell, maybe you could just see by looking that this was going to be a 1. Other times you would just go through this algebraic process. So now I still haven't found my limits yet. Not necessarily. I found actually some of them, but not all of it. So I'm going to move on to step 2, my y limits. I'm going to draw a vertical line through my region. Doesn't really matter where you draw it. I wouldn't draw it on an end point. I would draw it somewhere in the middle here. So any vertical line here. And I'm interested in where it enters my region R and then leaves my region R. And that's going to be my lower and upper limits for integration. And so I have to figure out, well, what y value is this? And then this one here, it looks like it's 1, but it's really not. It's close to it. What y value is that? This lower one came from this diagonal line. So all you have to do is, since it came from this diagonal line, is solve this equation of that line for y, which we actually already did. So this lower boundary is y equals 1 minus x. And then the upper boundary, this is the circle, the portion of a circle. And so you're going to solve this boundary for y as well. So on this one, I'm going to take x squared and subtract it. So y squared equals 1 minus x squared. And then I want y, so I have to square root both sides. Now technically when you square root, you're going to put a plus and minus here. And then you just pick the sign depending on where you're at with your region. And so for us, y equals the positive square root, because we're up here. We're in the positive range for y. We're not underneath the x-axis. Positive square root 1 minus x squared. So that's going to be where we leave our region. So y equals 1 minus x squared. And so our integration, how our integration would end up looking, let me just write it down for you. We won't go ahead and solve this, we'll just set it up. The volume of a function bounded by, let's say, f of x, y, and this over this region will look like the following. Okay, so our integrand, we would have some function given to us. Notice your boundaries for y depend on x, so that's sort of the giveaway that you have to integrate with respect to y first. But we already discussed it there. But the giveaway that this is going to go first is because it has x's in it. So if you integrate with respect to y after, you're still going to have x's left, and you don't want that, you want numbers left. And so you integrate with respect to x later. And so x, let's look at that. X goes from 0 to 1. So x is bounded from 0 to 1. And then y is bounded on the bottom by 1 minus x, and on top by root 1 minus x squared. And then that's how you would find your limits of integration. Now we'll do this again using horizontal cross sections. So now you're going to be using horizontal cross sections. So everything kind of just swaps. X is going to be integrated first, then y is going to be second. So the process is pretty much the same. You're just switching x and y and vertical to horizontal. So you're finding your x limits first, marking the x values where horizontal lines enter and leave your region, and then the y limits after by thinking about how you can contain all the horizontal lines. So same region we already looked at, we're just going to integrate the other direction. And so I want to start, we've already done step 1, I want to start by drawing my horizontal line. It doesn't really matter where, let's just pick right here. Okay, and a horizontal line that enters and leaves my region. Okay. And I'm just drawing an arrow to let you know, like, this is the lower boundary. My left boundary, this is a smaller x number, this is a higher x number, so this is lower and higher. Okay, in this case left and right. Now my y values, let's just look at those really quick. So we're going to integrate with respect to y second, but let's go ahead and just write that down. All my horizontal lines would be in between y is 0 and 1. So let's just get that out of the way real quick. Okay, so y is second. So x, this point here, well, what is that x value is the question. And so this x coordinate, well, it's on this slanted line, which we know is x plus y is 1. So you just have to solve this for x. And so if you solve for x, you get x is 1 minus y. And then we would leave our region right here at our circle, our partial circle, and the x value here will solve this circle equation for x. So if you subtract y squared and then square root both sides, you're going to get x equals positive square root, let me move this one out of the way, positive square root of 1 minus y squared. Again, technically you would have a plus and minus here, but we picked the positive because of where we're at. The positive x is over here. So this is our outer boundary or upper boundary for our limits. And so for our integration, our lower limit is x equals 1 minus y, and our upper limit is x equals root 1 minus y squared. And then whatever our bounding function at the top is, our z function. I want to discuss a couple of properties of double integrals with you. And we're going to do an example of the second one here. So the first property is called domination. And basically, if you know about two functions and how they behave on a region R, you actually know about how their double integrals behave. So if you know that the function f of xy is greater than or equal to this function g of xy on your region R, then you can conclude that the double integral of f of xy is actually going to be a greater value than the double integral of g over that function, over that region R. The additivity property, this one's pretty interesting, and we'll do an example of this. If R, or your region, is a union of two non-overlapping regions, R1 and R2, then your double integral can actually be broken apart. And you can take the double integral over one region, R1, plus the double integral over your second region, R2, and because these two regions make up R, then when you add these double integrals, it's the value of the double integral over the whole region R. Alright, let's look at this example. We're just going to take a look at the region, and this is going to be an example of the additive property we just discussed. So consider a region that's enclosed by this parabola, y equals x squared, and then this line y equals x plus 2. So let's draw our sketch real quick. Now, our parabola, y equals x squared, looks like our standard parabola, just like this, roughly. Okay. And then the line y equals x plus 2, our y-intercept is up here at 2, and then our slope is 1, so we rise and run 1, and we can draw some points or do a rough sketch of this. It's going to look like this. Okay. Could have been better, but not too bad. Alright, so we end up having our regions, or our boundaries meet right here. So the problem is about this interior region. Let me just make this a little bit more clear. So this is R. It's going to be enclosed by this parabola on the bottom side and this line on the top side. So this is R, down in here. Okay, so now, depending on how you decide to integrate, one way is going to be a little bit easier than the other. I'm going to show you the harder way. If we decide to integrate with respect to x first, let's see what happens there. Now, if you think about x, if I start to draw horizontal lines, this is going to be an example where I need to break this into two regions, and here's why. If I pick a horizontal line right here, okay, I enter at the parabola, and then I exit at the parabola. But let's say I draw my horizontal line higher. Well, I enter at the line, the diagonal line, and I exit at the parabola. Those are different. It's not the same entry point depending on where I picked my line. And so this is an example where you would have to break this into two regions. And so where you would break it apart is where they would change. And so right here, where the entry boundary would be the line, that's where we switch. So this bottom half, we'll call this R1, and this upper half, we'll call this R2, or upper portion. And so you have to just find your limits of integration separately for R1 and for R2. And so let's go ahead and figure this out for R1. R1, you enter and exit at the parabola. So you're thinking about, and this is for R1, what's happening with X? Okay, what's my lower and upper boundaries here? In this case, left and right. So our parabola, y equals x squared. Well, I want to know how this affects x. So I'm going to solve this for x. And so I'm going to take the square root of both sides, but I need a plus and minus. So I know that x is plus and minus square root y. Now, depending on where we're at, we're going to pick the plus or minus. Over here, our x values are negative, so this entry point is negative square root y. And then over here, our x values are positive, and so we exit at positive square root y. And so these are going to be our boundaries for x. And then our y boundaries for R1, well, we'd have to figure out where these two boundary lines meet. And so you can substitute. We did an example like this a little while ago, where we would just substitute, let's say, maybe this function into that one. And you would end up with x, so I'll just write this out really quick. If I substitute here, I get x plus 2 equals x squared. And then I can solve for x to figure out these meeting points. And if you solve this, you'll end up getting that this is at negative 1 for x and 2 for x. Okay? And then to get your y value, you can plug it back into either function. So let's just plug it back in right here. If I plug in negative 1 for x, y is positive 1. Plug in 2 for x, y is 4. Okay? So my y boundaries, using R1 region, y is going in between, let's see, for R1, just focus on this bottom part, 0 all the way up to 1. So y is bounded between 0 and 1. Okay? So our double integral here, over our entire region R of some function f of xy dA, we're going to break it apart into two double integrals, the first one being over R1. And so R1, actually let me just write it in this same step. This is going to give you R1 here. For x, the boundaries depend on y, so that's first, that's inside. So the bottom boundary is negative root y, upper boundary is square root y, and we integrate with respect to x first, and then y is between 0 and 1. In respect to y, we integrate second. And then we would add the double integral over the second region, R2. Okay, let me give myself some more space here. Now R2, you enter R2 on this line. Well, this line was y equals x plus 2. So if you solve this for x, you get y minus 2. So for R2, we know that x, you enter at y minus 2. And then you exit at the parabola, the positive part of the parabola, so square root y. And then y, for R2, y is as low as 1 and as high as 4. So y is bounded between 1 and 4. So inside here, we integrate with respect to x first, so y minus 2 up to square root y of f of x dx, dx first, and then with respect to y second, between 1 and 4. And so this is one way to figure out our double integral over this region. Now the other option would be to use vertical lines, and that would actually have been the easier option. I'll just point it out to you, we won't go through it. But if you had just picked a regular vertical line to begin with, no matter where you pick your vertical line, you would have entered at the parabola and exited at the diagonal line. So it would have just been a single double integral instead of the sum of two separate ones, had we chosen to integrate with respect to y first.